No short circuit. What? Hey guys, welcome back. Well, spring is close, but not here yet, but close. But at least we're getting more power. Today we got 13 kilowatt hours, just about. But today we are reviewing the Yixiang 12V DIY battery kit. Let's take a look. And here it is in all its glory. I have to say, first impressions, it's a pretty nice little box. Just hope the inside is as good as the outside. Let's see, we got rounded corners. It's only got single terminals, not the doubles. It's got the comms, RS485 in your can. It's got the, I think this is the 3.25 inch screen. Here you'll see something that we don't see on all the batteries. This is like an accessory port here. We got a 12 volt car adapter outlet. And we have a Anderson connector. So you can charge or discharge with this, but provided your charger puts out at least 13.8 volts, no more than 14.6 volts. But it's probably more for accessories, for like powering devices than actually charging. But you could do both, because I believe it's wired directly to the battery terminals inside, which brings up another point, but we'll cover that later. Looking at the handles on the side, they're centered, right in the center. Nice. Got your latches, so you can stack these in these 4 holes. The feet on the bottom are just these Allen bolts. Nothing fancy on this side, same thing. It's got the JK, oh, they put the sticker right here for the JK BMS. Oh, it's the 1 amp balancer, 200 amp continuous, 350 amp surge, and this is the 4-8. So the length is 17.5 inches. The height is exactly 10 inches. And the width is just under 8 3/4. If I compare this to my SFK battery, 12 volts as well, you can see the width is about an inch. This one's about an inch shorter in width. And the length is this is about 4 inches longer. The height is only about quarter inch, no, about half an inch taller for this one. So this is much much longer for the BMS, which sits right here. Yeah, this SFK battery is about the smallest form factor you can get for a 280 amp hour. You could even put 312 amp hour cells in here. This box weighs 25 pounds, just under. Let's take a look inside. A couple months ago, I reviewed the 24 volt DIY battery kit, and in it I found that the mounting tabs used to mount the epoxy board to the PCB rails, the screws were hitting the bus bars, causing a short. So let's hope that this battery kit does not have the same issue. Okay, so the first thing you'll be met with is the fire extinguishing aerosol, and it sits right in the BMS compartment right here. Look how long this bus bar is. It goes clear from the front all the way to the back. That's because the 4 cells that we install in this box will be single file like this. Okay, looking inside the BMS compartment, we see the same bus bars that we've seen on other batteries, and the M6 screws torqued and marked on both sides, so that's nice. You can see we have 2 lugs plus the bus bar. This one powers the BMS, and this lug is joined in with 2 wires. It looks like a 8 gauge and a 13 gauge, which supply the outlets over on the side of the box. Now these are siliconized wires, however, there should at least be a fuse on this 13 gauge wire. There's no fuse going to these accessory outlets on the side. So it's got the full potential of the BMS 200 amps right here at the terminals. So, and here is the front where I removed the accessory plate. Yeah, there's a decent amount of space in this compartment, but it always makes me nervous when You got the main positive and the main negative running so close together. It just makes me a little nervous. Everything kind of packed together. Let's go ahead and pop out the display. See if I can get a closer shot of all the bus bars and stuff over there. There's the comms board right down there. And the other side of the fuse over there, going up to the positive bus bar there. Looking at the fuse, I'll just remove this cover here. It is a mega style fuse, and it is a 200 amp fuse. Now, I don't know the AIC value typically for mega fuses. They're 2000 amps. I'll see if I can post the specs on the screen. So yeah, if you had a 2000 watt inverter and you were to drain this battery down to the bottom 2.50 volts per cell times 4, that's 10 volts. So just 2000 watts can push this thing to 200 amps. Personally, I don't like to push any of my batteries that hard, no matter the battery voltage. However, because this is a 12 volt battery, very easy to get to 200 amps. Unlike the 48 volt counterparts, it would take 10,000 watts to get one of those to 200 amps. Very hard. Now I do have this T-class fuse. Which does happen to fit the profile of the mega fuse exactly. So perhaps in another video we'll have to replace and update this fuse. But for now I want to test it as is from the factory. Alright, Yixiang 12V is the model number, 314 amp hour. Okay, right here. Maximum charge current, 150 amps. Standard discharge current, 100 amps. And continuous, 150 amps. And also, we can see with the over current, we got 151 and 155 respectively. So to me, I'm assuming that the first version of this battery kit, when it first came out, used the 150 amp JK BMS, not the 200 amp. So a 200 amp fuse on a 150 amp JK BMS would be sufficient. Since then, they've upgraded to the 200 amp JK BMS, but did not upgrade the fuse. Yeah, so with that said, 250 amps for the 12 volt battery. Let's take a look inside the cell compartment. Alright, so the first thing you'll be met with is the PCB rail. Let's pop off the BMS connector. We have 4 balance leads and 1 temperature sensor. We can see all the connections, all the solder connections are covered with glue, so that's nice. Let's see if we can get the BMS out of here. So we can see exactly how things are wired up. So you got these 8-gauge wires on the Anderson connector connected over to the BMS bus bar, directly to the BMS here. And this little pigtail comes off and goes to the car adapter connector here. We can see here we have the newer style JK BMS. This supports the RS485 and CAN bus communications. So we'll try to see if we can connect this up to the bus over there and communicate with the other batteries. We can see that the bus bars are taking well advantage of the mating surface on the BMS and are screwed down with 2 number 6 bolts on either side. So that's very nice. You can see that the BMS comes with these 2 temp sensors attached to the BMS itself. And then we also have the one on the PCB rail. So these ones are just kind of floating around in here. I guess you can put them wherever you like. So it'll be interesting if in the BMS software on the mobile app, if it's going to register 2 sensors or 3 sensors. What's in the box? The accessory box for the BMS. In it, we're going to have bus bars, our bolts for the cells, our terminal covers, an extra set of balance leads, and some zip ties. And next we have our PCB set with a piece of EVA tape for the PCB rail. Okay, taking a look inside the box, it's pretty standard Yixiang quality. It's a good build, nice thick metal and sturdy. We got a solid surface here for the cell to lay flat against, or to push against rather, on the front and back. So that's good compression support for the cells. Looking at the epoxy board, you're going to have one piece that has this notch, and I'm not sure what this is for yet, but I'm sure it'll become apparent. It should sink down just like that, kind of by itself, with a little bit of force. I'll put the polarity on the screen so you can see the cell layout right here. And I have an issue with this type of bolt for the 12-volt battery, and I'll tell you why. As you can see here, I have oodles of these bolts because I prefer not to use them on a 12-volt battery. I prefer to use this one, the serrated head. Now the reason I prefer this one over this one, because this one tends to build up heat. I'm not sure if it's the lock washer or the construction of the bolt or the material used, but this one does a better job at mitigating the heat near the terminals on the battery cells. I have a video where I tested this and I can show you the heat difference between these two bolts. I'll post that right here. Now for the larger batteries, the 48-volt batteries, these are fine because it's very rare that you're going to pull 200 amps. To our main negative. Perfect. Oh my God. Again, Yixiang, what is up with this? Both on the 24-volt and now the 12-volt kit. The mounting tab with the screw is directly over the bus bar. If the screw goes through here and penetrates this insulation, it will cause a short. Again here. These two are okay. These tabs need to be here, here, not over the bus bars. Let's actually see how bad it is. These are the screws they give you, and they only give you two, ironically, for these two, right? You don't want to use these at all. Just completely avoid these two tabs. But let's see how bad it is. Well, it's not touching, but it is damn close. All right, now that I flipped the bus bars, there's much more clearance there. Let's take a look. Not sure if you can see it. Yeah, so there's about half an inch of clearance there. So it's funny because on the 24-volt battery DIY kit I reviewed, they had the same problem, and one of the commenters said it was my problem. This is not my problem. This is clearly a design flaw. I should not have to verify the length of the screw from the manufacturer that if it's going to go through in contact and pierce the insulation of the bus bar and cause a short. So we'll do our temp sensor first. Our negative BMS lead. Now one thing that's nice about these screws with lock washer is when they tighten the balance leads, they will not rotate the balance lead. They'll stay there. 6.5 Newton meters. I like to go a little high. Should get about 13 volts. There we go, 13 volts. Perfect. And we'll just tuck the excess behind the BMS. Epoxy board. Placed. Bus bar through the hole. This part will take a little bit of finesse. I've done it 4 times already. Done. Now for the fire extinguishing aerosol. And we can close the lid. All right, we have power, 13.1 volts. We have air 9, so we need to go in there and configure the BMS. Okay, so there's a few things we have to configure inside the BMS. First, we need to go in and verify a password. 1, 2, 3, 4, 5, 6. We have to set the battery type, it's LiPo 4. And then we need to set the cell count to 4, since it's a 12 volt battery. Then we need to set our battery capacity to 300 amp hours. Continued discharge current, 200 amps. Overcurrent protection delay, 300 seconds. That's way too long. Set that for 10 seconds. And then if that occurs, if we hit an OCP, it's going to re-engage the BMS after 60 seconds. That's pretty much the minimum settings that you have to do. Charge current's a little low, we can up that. Okay, we should be good to go. We have all 4 cells registered. Battery T1 and T2. So there's only 2 temp sensors. So we're going to have to investigate whether the one on the PCB is actually being used or not. So you can see right here on the rail, on the PCB rail, the temp sensor is labeled NTC1. If you come over here to the pinout on the connector, you can see NTC1 is empty, not connected. So apparently the temp sensor on the PCB rail does absolutely nothing. Perhaps they should change it to NC1, not connected one. Or maybe NTC1 means not connected one. I don't know. Since this is not a retail battery, it is more of a DIY battery, I'm not surprised that you have to come in here and configure the BMS. I've built a lot of batteries and I'm actually quite used to it. However, if you're new to building batteries, it would be nice if they had a pre-configured profile. Because on these JK BMSs from the factory, from the JK factory, not Yixiang, the default is LTO and it's going to set it to 8 cells. So that's a 24 volt battery. If this was a retail battery, you would expect to have a pre-configured profile so that the user would not have to mess with these settings. Okay, so we're going to do a low temp and a high temp cutoff test on these temp sensors. So in the BMS settings, the under temperature protection return is 0 Celsius. So we need to put that to, say, 1 Celsius. And then the under temperature protection is negative 10 Celsius, so that's too cold. Let's put that to 0. And let's test it out. Okay, I got our glass of ice water and I got the temp sensor in the ice water. And we're currently at 0.8 Celsius on T2, so we need a little bit more. I don't think my water is cold enough. Put our return to 2 and our UTP to 1. One 1.2. 1.0. There's our alarm. Protection, charge under temp. So that works. Let's warm it back up and see if it clears the alarm. There it goes, alarm is cleared. Works good. Let's see if T1 responds in the same way. We're just looking for it to drop. Yep, it's dropping fast. So these temp sensors are probably both low and high temp. Okay, so our high temp value is set at 70 degrees Celsius and our return is 60 degrees Celsius. We should get alarm. There's our alarm. Protection charge over temp. Let's cool them off. It's already cleared, so we're good. High temp and low temp work perfect. All right, so what I want to do now is see if we can simulate a short circuit on the car adapter outlet and see what happens to that 13 gauge wire inside. Since there's no fuse on that wire, we're going to have to rely on the BMS to step in and save the day. There's 2 ways the BMS can do this. You can do it by overcurrent protection or short circuit protection. Now, since the delay on the overcurrent protection is set to 10 seconds, I think that's far too long for that small of wire. It might melt before the BMS actually kicks in, so I'm expecting the short circuit protection to kick in on this one. Now, I got this car adapter plug with bare wires. It came with a 10 amp fuse already, which I blew. So we're going to swap that fuse for a 30 amp fuse and see what happens. This thing is rather janky. So there's the 30 amp fuse. Oh no, that's the 10 amp. I thought I already swapped it. And that's the 30. You can see how much larger the wire is inside. Oh, does it not fit? Oh no. Yeah, that one's a lot thicker. I think we can jam it in there. Here we go. I didn't think this had a fuse until I tested it. Alright. Okay, here's the 13 gauge wire right here. So we'll keep an eye on that. We're going to watch the BMS for a short circuit error. Plug it in. Now, typically it takes, I think, around 20 amps, I think, to do it. It's just a matter of how long can it do it before the fuse pops. So, let's see what happens. Fuse is gone. Nope, it's still going. Ooh, 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 it's getting hot. Man, it's not pulling enough current. Do something crazy. This thing is smoking. This 13 gauge wire is rated for 200C. Alright, I'm going to pre-twist the wires here. I think these wires are just going to burn up. Alright, here we go. Plug it in. We're drawing 30 amps. This wire's smoking. No short circuit. Come on. Nope, the fuse died. This thing is smoking. That's a one-time use, eh? So we couldn't draw enough amps to short circuit the car adapter socket. Oh, it's like melted into the plastic. I can't even get it out. Oh, look at it. Oh. What? Wow, that thing's smoked. Alright, so we got to prove that the short circuit actually does work on this thing. So we're just going to short circuit the terminals directly, and we're going to watch our BMS. There it is. There's our alarm. Protection, discharge, short circuit. And it will return in 20 seconds. So I think what happened there with this wire is so thin that it just ends up dissipating as heat, and it creates a high resistance scenario versus the terminals, which is a low resistance scenario, and that's what the BMS looks for in order to determine if it's a short circuit. Even though that 13 gauge wire could probably handle 200 amps just for a few minutes, just long enough to destroy your device. So if this was your device plugged into this battery, it would burn up before the battery did anything about it. So we need a fuse inside the battery on that small 13 gauge wire. Okay, we got the battery connected up to the 12 volt system. We're going to try to pull exactly 200 amps continuous. Hopefully we don't blow that fuse. I'm waiting for this thing to kick in. 180 amps right now, about 190. 199 exactly. We're going to hold this for about 10 minutes. We'll be back. We were just about 5 minutes in. I was going to do a heat recording, and we hit the discharge overcurrent protection. So we held just over 200 amps for a little too long because the battery voltage is dropping. So now I dropped it to about 190. We'll come back in 5 minutes. Crap. No. So we're going to take a look at heat stress in the battery. You can see the battery, is that the bus bar is hitting about 125 degrees. 130 over there. Wow, 100, what is that? 162. Well, 192. Is that on the fuse? I think that's on the fuse terminal. 192. Wow. Man, 200 degrees on that fuse. 204. All right, next we're gonna purposely drive up the current and we're gonna see if we can surpass and trigger the overcurrent protection. 194, 195, 200. Hopefully we don't blow the fuse in there. 206, 205, 208, 214. There's your alarm. So we got discharge over current, and we did not blow the fuse. You're looking at the bus bar that goes down to the fuse. This part is extremely hot right there, where it contacts the fuse terminal right there. And it's superheating the bus bar all the way up, and as it travels down the bus bar, it gets cooler and cooler and cooler and cooler all the way to back here, and this is the coolest point. And that's the problem with these mega fuses. They got a very thin terminal. So all that current is forced to go through that terminal, causing a lot of heat. If you look at a Class T fuse, look how thick that is. That can carry 200 amps continuous. And that's why we need to start seeing Class T fuses inside these batteries, especially the 12-volt batteries. This will give us a higher AIC value and help to mitigate heat. Okay, final thoughts on this battery, starting with the good. We have a good, solid, sturdy box of good quality build. We have an internal fire extinguisher. We have a fuse. And we have flexible bus bars. The cable they use for the accessory outlet is actually quite nice. It's siliconized and it's good for 200 degrees Celsius. So it's a very good cable at least. The things that need to be addressed or fixed. The epoxy board mounting tabs on the PCB rails need to be relocated to avoid a potential short. The 13 gauge wire feeding the car adapter outlet needs to be fused. The main fuse should be upgraded to a 250 amp fuse because we have a 200 amp BMS. It would be nice if it was a Class T fuse. That would help with heat mitigation. The temp sensor located on the PCB rail needs to actually do something, and there needs to be 2 of them. The main display on the front is not secured very well. I had to glue it in place to keep it from popping out. Things that would be nice to have. By the looks of it, having these ports, this battery seems to be more of a utility battery, like you're going to move it around a lot in a mobile application. The handles are a bit unbalanced where they're located in the center on the sides of the battery. When you lift it up, it tends to lean to the back. It's a bit awkward. If the handles were on the front and back, it'd be very easy to lift and move around. Okay, talking about the bus bars, I'd like to see more space and better pathing for the main negative and main positive. And maybe instead of using this bus bar for a main positive, use a battery cable instead with some thick insulation. Okay, so I prefer a metal case over plastic ABS any day. So I think what we're going to do is we're going to do another video and we're going to make Yixiang safe again. I think we can make this into a good utility battery. So what we're going to do is we're going to replace the car adapter with a USB outlet. We're going to add a fuse, we're going to upgrade the main fuse, and we're going to add a built-in charge controller because we have a lot of space here. So that'll be cool. Alright, that's it for this video. If you don't want to wait till the next one, check out this video right here and I'll see you on the next one.